Welcome back. We're continuing our study of the history of software-defined networks. In this lesson, we'll talk about the history of active networks. We will talk about what active networks are, the motivation for active networks, and the technology that supports active networks. We'll also talk about how active networks relate to software-defined networks, as well as the legacy of active networks for SDN. To remind you where we are in this module, we just completed a lesson on the history of central network control, which dates back at least to the 1980s and AT&T's network control point. We're now going to study the origins of network programmability, in particular its roots in the active networks projects of the 1990s. So first of all, what are active networks? Simply put, active networks are networks where the switches perform custom computations on packets as the packets travel through those switches. Some examples. You might imagine a router or every router in the network performing some kind of tracing or a program on the packets as they travel through the routers. Middle boxes are also an example of active networks. Boxes in the network that perform firewalling function, proxying, application services, and so forth are all custom computations on traffic that are performed in the network. And we can think of middle boxes as a modern day form of active networks. Where did active networks come from? Well, in the mid-1990s, the DARPA research community was discussing various problems that existed in today's networks. In particular, they identified that it was very difficult to integrate new technology into the network, and that sometimes the network would exhibit poor performance because the same operations were being re-implemented at multiple layers of the protocol stack. Finally, it was noted that it was difficult to accommodate new services as they're introduced into the network. So in a nutshell, the motivation for active networks was to accelerate innovation. It was observed that innovation relies on consensus, and that from the time at which a working prototype was demonstrated to the time at which that technology would ultimately be deployed in an operational network could take as long as 10 years because of standardization, the process of procuring new hardware, and ultimately testing and deploying it in a production network could just take forever. If that motivation sounds familiar, it's because SDN actually has the same motivation. That is, accelerating innovation in existing networks so that technology could be introduced a lot more rapidly without consensus, standardization, etc. Well, active networks had the same motivation and observed that if you could put active nodes in the network where routers could download new services into the infrastructure, that could allow for some user-driven innovation. So the main idea here is that messages or packets would carry both the data and procedures that might operate on that data. So these active routers that perform these custom operations might coexist with legacy routers that do nothing more than forward the traffic. Each of these programmable switches might then perform additional processing in addition to forwarding the traffic. So there were both user demands and technology enablers that made active networks compelling at the time. On one side of the coin, the demand side, the proliferation of firewalls, proxies, transcoders, etc. resulted in a lot of ad hoc point solutions to solving various custom packet processing problems. And the goal or the vision of active networks was to replace a lot of these ad hoc approaches with a more unified approach. On the flip side, we had technology push or enablers. There was a lot of research and technology being developed at the time in support of safe execution of mobile code. In particular, Java applets were emerging, and those provided the ability to develop portable code that could run in one place or another, and it allowed shipping code around, which was a very natural supporting technology for certain types of active networks. Also, various operating system support was being developed. The Scout operating system focused on support for real-time communications. The exokernel developed new technologies to allow safe access to low-level resources, and Spin focused on providing trustworthy code or providing technologies that could enable generation of the trustworthy code. So there are two different approaches to active networks. The first was a rather extreme approach, and that was essentially that every message or every packet actually carried a program. And active nodes along the network path would evaluate that code that was being carried in the packet. So the code, as it was carried in the packet, would be dispatched into an execution environment that was running on a programmable switch or router. We'll take a look at capsules in a little bit more detail on the next slide. But the other approach was something that looks a lot more familiar to us now and almost looks like SDN. And the idea here is that you could have programmable switches where code would be installed. Those programmable switches then would perform custom operations or processing functions on packets depending on values in the packet header field. So essentially, packets would be dispatched to the appropriate code block depending on the values of packet headers. So that sounds a lot like SDN. You wouldn't be mistaken. Let's just take a quick look at capsules. So capsules essentially expand the existing packet header. So in addition to having the regular IP header with your payload, you would have an active networking header. And this particular one was the ANTS header. This was developed at MIT. And this header actually had a few additional fields. One was the type, which specified the forwarding routine to be executed, in particular code by reference. The previous address basically told the node where to obtain the forwarding routine if it wasn't available on the present node. The dependent fields allowed the packet to pass parameters into this code. And then, of course, there was the payload itself. So some previous notable projects in active networks. One was the ANTS project, which we just referred to, and that actually took the packet capsule approach, where Java programs would actually be carried with these packets. Naturally, this introduced some limitations for guaranteeing quality of service, and in response to that, the University of Arizona had implemented something called the JAWS JVM, which provided better real-time performance for active network scenarios. There was also the switchware program at Penn, which developed a programmable switch and a scripting language that could support the invocation of switchlets. The Smart Packets project at BBN focused on applying active networks to network management problems. Open Signaling at Columbia developed a language called NetScript, which allowed a programmer to specify custom packet processing routines and pipelines on streams of packets. We will look at some more modern programmable data planes later on in this course that look a lot like Open Signaling. Finally, there was the Tempest project at Cambridge, which invented something called switchlets, which was a programmable, virtualizable switch, and we'll look a little bit more at that in the next lesson. So what happened to active networks? This technology was introduced almost 20 years ago. Why didn't we see some of these ideas come to fruition sooner? Well, for one, the timing was off. At the time, there was no clear application for this type of programmability. As we've seen now, and as we'll see throughout this course, one of the killer apps or killer environments for SDN was the data center and the cloud. And at the time, the data center and cloud just didn't exist. So there was no particularly clear application for active networks, at least no immediate application. Additionally, hardware support wasn't cheap. Everyone was using ASICs to support this type of technology. Now we have a lot more options to support programmable data planes, such as TCAMs, FPGAs, and network processors. There were also some missteps. In particular, there was a lot of focus on security, providing special languages for safe code, talking about packets that carry code, etc., and maybe too much focus on this as opposed to the general concept or the overall goal of how do we provide programmability in the network. So whether or not it's done by a capsule or whether or not it's done by a programmable switch was less important than simply providing that programmability or flexibility in the infrastructure. There was also potentially too much focus on the end user, people like you and me sitting at our laptops or end user devices in our homes as the programmer. In contrast, SDN has now focused on the network operator as the programmer, or the application service operator, people who actually want to introduce new technology into the network. Finally, there was a lot of focus on interoperability between existing active network implementations and deployments. And in contrast to that, OpenFlow essentially punted that. They did a very good job with grappling with backwards compatibility in existing switch hardware. It was it's effectively a simple firmware upgrade to provide OpenFlow support into existing switches, and many switch hardware platforms already support these basic operations that OpenFlow specifies. So let's just think about the legacy of active networks for SDN for just a minute. What lessons can we take away from active networks? Well, the first was the idea of providing programmable functions in the network to enable innovation. That problem statement, or that motivation, is almost identical to the SDN motivation, and it has roots in active networks. The second was that idea, the programmable switch approach, where switches would actually carry code, or code could be installed on switches, and then the packets or values in the packet headers would determine how those packets would be demultiplexed into the correct code block. That idea actually came from active networks, and we've seen it over and over and over again in projects like Planet Lab, FlowVisor, Genie, even now all the work talking about how to integrate SDN with middle boxes. It all has roots back into this idea that came from active networks. Finally, just one more point on middle boxes. It's worth noting that active networks paid a lot of attention to middle boxes. One of the motivations for active networks was the proliferation of different kinds of middle boxes and the vision for a unifying architecture. So we're now seeing the same type of vision being espoused in various SDN projects, and it's probably worth going back to look at some of the work on active networks to see whether or not some of the same lessons that were learned there could be applied to integration of middle boxes with SDN. Welcome back. We are continuing our discussion of the history of software-defined networks. Today we'll talk about network virtualization. We'll first talk about what network virtualization is and what it's useful for, and we'll trace its history back to the 1990s, as well as exploring some of the developments of network virtualization over the past 10 years in the form of both support for network experimentation, as well as various concepts such as the separation of service providers from infrastructure providers that we saw in some earlier network architectures. We'll also look forward and talk about how network virtualization relates to software-defined networks. So to remind you where we are in the third of 3 lessons where we're discussing the evolution of supporting technologies. We just finished our discussion of the history of network programmability, and we also talked about the history of central network control. In this lesson, we will talk about the history of network virtualization. So first of all, what is network virtualization? Simply put, network virtualization is the representation of one or more logical network topologies on top of the same underlying physical infrastructure. And there are many different instantiations of network virtualization, some of them that predate even the 1990s, such as virtual LANs. What we're going to talk about in this lesson, however, are various technologies and network testbeds that used and developed network virtualization since then that have essentially led to some of the more mature virtual network technologies that we see in the form of companies and commercial products today. So first of all, what are the benefits of network virtualization? One of them is sharing. So using network virtualization, one can instantiate multiple logical routers on top of a single physical node or a single platform. And more generally, one can instantiate multiple virtual networks on top of the same physical network infrastructure. This sharing, of course, requires the ability to provide resource isolation in terms of CPU, memory, bandwidth, forwarding tables, and so forth. So in addition to sharing, network virtualization offers the prospect of customizability. Users of a virtual network could essentially get a view of their own logical network and logical network topology that's separate from other logical networks that may be running on the same underlying physical infrastructure. And the ability to see an independent logical network also allows the ability to run custom routing and forwarding software on that particular slice of the virtual network. So let's just look at what this might look like in terms of a few pictures. So let's assume we have a fixed physical infrastructure, and on top of that fixed physical infrastructure, the routers, links, and so forth, we might have multiple parties who want to use that fixed physical infrastructure. So we might have the red party and we might have the blue party, each of which might want access to different underlying physical network resources. Each of those parties might also want to instantiate different arbitrary virtual topologies on top of that underlying physical infrastructure. So the idea here is that each of these parties who wants to use the infrastructure has the ability to create their own view, or their own virtual topology, or own logical topology sitting on top of that physical infrastructure. And the idea is that each of these would be able to run independently without interfering with one another. So in the rest of this lesson, we will explore three different examples of virtual networks. One is the Tempest architecture, or switchlets, which dates back to the late 1990s. And some of the ideas that came out of switchlets are the separation of the control framework from the underlying switches themselves, as well as the ability or capability to virtualize the underlying switch hardware to provide the appearance of multiple virtual switches. The second virtual network technology that we'll look at is something called the virtual network infrastructure, or VINI, which dates back to 2006, and the motivation here was to provide a virtual network infrastructure so that experimenters could run experiments with their own logical networks shared on the same underlying physical topology. Then we'll look at a network architecture called CABO, which used some of the vision of the emerging virtual network technologies to realize that virtual networks could allow service providers to operate independently of the providers that make the underlying physical network infrastructure available. So let's first look at switchlets, which came out of something called the Tempest architecture. In this particular architecture, we have a single underlying switch with its resources, and then we have an open switch control interface that exposes those resources to software that's sitting above. Indeed, that control interface does look a little bit like OpenFlow. So the idea or the motivation behind switchlets was to allow multiple control architectures to operate over a single ATM network. The open control interface separated the switch controller and the fabric via an open signaling protocol, and the divider partitioned the switch resources to allow multiple controllers each to have their own view of a logical switch. Indeed, that looks a little bit like FlowVisor, something that we will explore a little bit more when we talk about modern SDN architectures, in particular OpenFlow. The switch divider partitioned port space, bandwidth, and buffers and allowed different controllers to control each switchlet. Now, in addition to the similarity of this architecture to some more modern SDN architectures, it's also interesting to note this paragraph in the conclusion of the paper that introduces the switchlet architecture. It says, as anyone can obtain a virtual network will effectively be a network operator, we hope to see an increase in the creativity that can be brought to bear upon the problem of network control. So that's interesting because it essentially predicts what happens next, which is the realization that virtual network infrastructures can allow network researchers to bridge the gap between small-scale experiments and simulation and real live deployments. And that was the motivation behind VINI, or the virtual network infrastructure. The idea here was that on one hand, we had controlled repeatable lab experiments that were potentially not so realistic, and on the other hand, we had live deployments which were very realistic, could scale up, run real traffic, but not necessarily be repeatable. And the idea here was that we could use network virtualization to bridge the gap between repeatability and realism. So VINI runs real routing software, exposes real realistic network conditions to the applications running on it. It gives control to the experimenter over different network events, such as failures. It can carry traffic on behalf of real users. It can also be shared among many different experimenters. Vinny also used a separation of the data and control planes to achieve some of its goals of network virtualization. Its control plane is a software router called Zorp, which runs a variety of different routing protocols with the goal of allowing the experimenter to run real routing protocols on top of virtual network topologies. Vinny's data plane provides the appearance of these virtual network topologies to experimenters. Vinny's data plane is implemented using a software router called Click, and the interfaces, the virtual interfaces, were implemented using a technology called tunneling, which is also used in many other virtual network technologies to create the appearance of virtual links. In Vinny, experimenters could also put filters in front of these tunnels to create the illusion or appearance of failing a link. These filters would essentially just block packets on individual tunnels. Given the technologies to build virtual networks, researchers then began exploring how this technology could be used to facilitate the introduction of new services and speed the pace of innovation. One of those architectures was called Cabo, or concurrent architectures are better than one. This architecture offered the insight that the infrastructure providers, or those parties that maintained routers, links, data centers, and other physical infrastructure, could operate independently or separately from the service providers that offered end-to-end services on top of that infrastructure. Examples of this separation between infrastructure and service providers in some sense already existed. Two such examples were Packet Fabric, which allowed multiple ISPs to share the same physical routers at exchange points, and Phone, a commercial internet service provider that resells users' wireless internet connectivity to its customers. Phone has an interesting economic refactoring where the users in their homes who buy upstream connectivity from different internet service providers are effectively the infrastructure providers, and Phone is simply a broker of that internet service and effectively acts as the service provider. So let's just summarize what we've learned in this lesson. We have learned about network virtualization, in particular what it is. Network virtualization separates the logical network that users or service providers see from the underlying physical infrastructure and potentially allows multiple parties to share that same underlying physical infrastructure for different purposes. Network virtualization has a rich history dating back to virtual switches or switchlets in the 1990s, network test beds such as Vinny, and these architectures that envision using network virtualization to offer different types of services. The legacy of network virtualization for SDN is actually quite rich. The idea of separating service providers from infrastructure providers is something that we see a lot in commercial software-defined networks today. The idea of using multiple controllers to control a single switch and exposing multiple logical switches on top of a single switch is actually something that has roots in the switchlets architecture, and the notion that a single physical infrastructure could in fact expose multiple logical network topologies also has its roots in a lot of this network virtualization research. So to summarize, we've just completed 3 lessons that explore supporting technologies for software-defined networks. Next, we will talk about different types of standardization of the control plane that were going on in parallel with the evolution of these supporting technologies. Welcome back to the course on software-defined networking. In this lesson, we'll be wrapping up our discussion of the history of software-defined networking, and in particular, we will explore the history of control of packet switch networks. We've already explored a little bit the history of central network control, but most of that was in the context of the phone network and circuit switch networks. And today we'll look at how the control of packet switch networks has evolved. I'll begin by reminding us why separating network control from the data plane is a good idea, and then we'll look at different ways that have been developed to control packet switch networks. We'll start by looking at the Forces protocol, which was developed in the Internet Engineering Task Force, which effectively defined a custom separate control channel to control switches or forwarding elements. Then we'll look at the routing control platform, which used an existing protocol, in particular the Border Gateway Protocol, to dictate or control the routing decisions or forwarding decisions that BGP-speaking routers in a backbone network made. Then we'll look at how the emergence of open hardware enabled the much more widespread adoption of separate control of packet switch networks. So first, let's remind ourselves why separate control is a good idea. First, it enables more rapid innovation since control logic isn't directly tied to the hardware. Second, it enables the controller to potentially see a network-wide view, thereby making it easier to infer and reason about network behavior. Finally, having a separate control channel makes it possible to have a separate software controller which facilitates the introduction of new services into the network much more easily. Let's now look at three different ways that were developed to control packet switch networks. The first instance of a separate control channel for packet switch networks came out of the Internet Engineering Task Force in the form of the Forces protocol. The protocol was first standardized in 2003, and there were three implementations of this particular standard. The standard essentially defined protocols that would allow multiple control elements to control forwarding elements, which would essentially be responsible for forwarding packets, metering, shaping, performing traffic classification, and so forth. So the idea was that these switches or forwarding elements could be controlled over a standard control channel called the Forces interface. And there might be multiple such controllers controlling the forwarding behavior of these forwarding elements. So this was all well and good, and in some ways it looks a lot like the OpenFlow standard that we know today. But the problem with this particular approach was that it required standardization, adoption by vendors, and deployment of new hardware. And these particular hurdles were the same hurdles that were the motivation for some of the earlier work, such as the active networks projects that we looked at. Another approach was to essentially use existing protocols as control channels, essentially hijacking existing routing protocols to send control messages to the forwarding elements. This approach was taken by the routing control platform. The idea was that every autonomous system or independently operated network might have a routing control platform, or an RCP, which would compute routes on behalf of the routers and then use the existing BGP protocols to communicate these routes to the routers. So the idea was that computation would happen up here in the RCP, but once the routes were computed, the results of that computation would be pushed into the router's forwarding tables by standard routing protocols. So these routers would be under the impression they were just speaking to any old router, but in fact they were speaking to a smart box that was actually computing the routes on their behalf. Using these existing in-band protocols to control a packet switch network effectively makes it easier to transition from the status quo to something where all of the control is centralized in a particular network. The RCP effectively used BGP as a control channel so that the forwarding elements thought that they were talking to just another router, but in fact all of the smarts for the network were centralized at a single point. This approach makes deployment somewhat easier since it doesn't require standardization on a new set of control protocols. However, the problem with the approach is that the control that one has over the network is constrained by what existing protocols like BGP can support. So effectively, the RCP was limited because all it could do is control BGP routing decisions, when in fact, a network operator might want to control a much wider range of behaviors. Ultimately, the architecture still proved useful, and a version of the RCP is currently running in at least one large backbone network today to do things like automated traffic redirection for security incidents or traffic scrubbing. But nevertheless, the range of applications that something like the RCP can support is still somewhat relatively limited in comparison to what might be possible with a general separate control plane. Customizing the hardware in the data plane potentially makes it easier to support a much wider range of applications in the control plane. The first project to realize this was the Ethane project, which presented a network architecture for the enterprise which allowed direct enforcement of a single fine-grained network policy at something called a domain controller. That domain controller would compute the flow tables that should be installed in each of the enterprise's switches based on the access control policies defined at the domain controller. Ethane required the deployment of custom switches, and the project implemented several of these based on OpenWRT, NetFPGA, and Linux. The problem with this approach, of course, is that it requires custom switches that support the Ethane protocol. So what we're looking for is something that gets us the best of both worlds, something that could operate on existing protocols yet wouldn't require customizing the hardware. The answer to that question was OpenFlow. And here the idea was to basically take the capabilities of existing hardware and open those up such that a standard control protocol could control the behavior of that hardware. In OpenFlow, a separate controller communicates with the switch's flow table to install forwarding table entries into the switch that control the forwarding behavior of the network. Because most switches already implemented flow tables, the only thing that was necessary to make OpenFlow a reality was to convince the switch vendors to open the interface to those flow tables so that a separate software controller could dictate what would be populated in those flow tables. So what have we learned about network control in this lesson? One of the lessons is that control and data planes should definitely be decoupled, because vertically integrated switches make it very difficult to introduce new control planes. In some sense, Forces looks a lot like OpenFlow, but because it required new standardization and adoption and changes to the hardware, deployment ultimately became very difficult. The second lesson is that using existing protocols makes deployment easier, but it also constrains what can be done, and we saw that in the RCP. Finally, we saw that open hardware can allow decoupling the control and can actually spur adoption. And this is potentially one of the reasons that made OpenFlow so incredibly successful relative to these other similar proposals.